Hey friends, it's Mrs. Diskevich, and this is a quick little review of ionization energy, the second periodic trend that we've been discussing in class. Ionization energy, the first thing we need to realize is that basically, if we give an electron enough energy, so when we say in the form of a photon, just like I said in class, remember photons, every single thing on Earth is either matter or energy. So photons is a form of energy in which energy can be transferred, and it's very, very small. It's like that's like the it moves in like a wave, and that's why we talk about wave mechanics and so forth in some chemistries. But if we give enough energy to overcome the effective nuclear charge, so remember the effective nuclear charge is when the nucleus is holding in those electrons because it has the effective nuclear charge can be a high number of protons, so it can be highly positive, holding in those negative electrons. Sometimes there can be enough energy where it's allowed to take away one of those electrons. When that happens, those electrons can leave the atom completely. So when that electron's left completely, therefore it's going to a different atom. So that means it has gone through enough ionization energy for that to happen. Then the atom has been ionized or charged. Now, we've talked about ions a lot so far. We know that when an atom loses an ion or when it loses an atom, it becomes a cation. Here's some cation examples here. If we have an atom that's gaining, so that electron's going to go somewhere. Those electrons are gaining electrons. They're going to become anions. So remember, we have anions and cations and all that good stuff. Anions are the ones that gain electrons. Cations are the ones that lose it. Don't forget that. The number of protons and electrons is no longer equal then. So let's take potassium, for example. Normal potassium, has 19 protons in its nucleus, 19 electrons around its nucleus. If potassium loses an electron, it's going to have 19 protons and 18 electrons now. So that ionization energy overcame this effective nuclear charge here to take away one of these electrons. And so therefore, there was enough ionization energy for that to happen, and it became 18 electrons instead. So really, a true definition for ionization energy then is the energy required to remove an electron from an atom. That is the actual ionization energy. And the ionization energy is measured in kilojoules. I want you guys to realize that kilojoules, not joules, kilojoules. So we're talking quite a lot of energy for this to happen. This is not an easy thing to happen. The larger the atom is, the easier its electrons are to remove. So that makes sense. Let's say, we have something like cesium that has electrons in the 6s sublevel. Well, if there's electrons in the 6s sublevel, it's going to be a whole lot easier to remove those because this 6s is going to be further from the nucleus. So when we have farther from the nucleus, these electrons are feeling less of an effective nuclear charge. So the ionization energy and the atomic radius are inversely proportional. What that means is as one goes up, the other goes down. So as the ionization energy increases, actually the atomic radius decreases. And as the atomic radius increases, the ionization energy decreases. We'll look at that in just 1 second when we go to the periodic table on the next slide. But ionization energy is always endothermic. So that means energy is added to the atom to remove the electron. So that's important to know in the future. If you have calcium and you have enough ionization energy to pull an electron away, therefore it gave calcium energy, it added to it, so it's endothermic. And if you recall, the opposite of endothermic is simply exothermic. That's when enough energy leaves an atom. Okay, looking at our periodic table, I just want to show you a couple things, and I want to make it in relationship to the atomic radius and ionization energy. So if you think about it, the atomic radius increases as we go down families, and the atomic radius also, it decreases as we move across the periodic table. So for the atomic radius, that occurs for, let's change color real quick and show the ionization energy. So the ionization energy is going to be very high as we move toward helium. So as we move toward helium, the ionization energy increases, the atomic radius actually decreases. As we move toward this side of the periodic table around the region of Francium, the ionization energy actually decreases and the atomic radius actually increases. So that's where the inverse relationship comes into play. Bottom line is, with the ionization energy, what I like to remember is He has a high IE. So that helps me remember helium has the highest ionization energy. Again, helium has the highest ionization energy because helium is not only a small element, meaning it only has 2 electrons, and those 2 electrons are in the 1s orbital, but it also, because the 1s orbital can only hold 2 electrons, it is full. So it's got a full valence shell. It's got full number of valence electrons. So therefore, it's going to be able to be very difficult. It's going to require lots and lots of energy to pull one of those electrons away. So ionization energy, again, the energy it takes to remove an electron. One thing, too, to remember, your first ionization energy might be high, for example, and your second might be very much lower. So let's think about 1 second. Let's go back here to our periodic table and let's think about potassium. Okay, potassium, it's going to take less energy to pull an electron from potassium. So therefore, potassium's first ionization energy is very low. However, once potassium loses an electron, it's going to be very much like argon. Argon, on the other hand, is going to be very difficult to take an electron away. So therefore, argon is going to have a high second ionization energy. So because potassium K plus is going to be like argon. So we have to think about this, and potassium's first ionization energy is low, but its second ionization energy, or the energy it takes to remove a second electron, is very high. We have to take this into consideration. So we can look at actually first ionization energy, second ionization energy, and in fact, third ionization energy, which we typically don't get to a whole lot. Okay, so make sure you ask questions in class and feel free to ask questions to compare ionization energy and atomic radius as well. All right, take care, guys.